Okay, so as you can see here within my HDL Designer software by Mentor Graphics, I've got my full project here on the symbol, and what I've done is I've essentially written all of this in one VHDL file. So I'm going to bring that up and we'll talk about the interfaces that I've got set up. So essentially here we have a single VHDL file, and I'm going to provide a link for you to download this and check out the code and manipulate it in your own way. Once we review it, you'll understand how the code works, and then that way you can go and create your own interfaces and specific input switches if you wish to do that, to control specific input signals to essentially declare which message that you have programmed within the VHDL code to be displayed on the screen. I'll have a link within the description of this video that's going to bring you to a devoted page on my website for this particular project, and it will have the download link for this VHDL file and other images and other information that applies specifically to this project, just to give you a real in-depth tutorial on how it all works and how it functions. So check out the link within the description of this video for the link to that. So now I'm going to talk about the interfaces here. We have our inputs and our outputs, and we essentially have our databus output that goes directly to the LCD display, and so we have the 8 bits there, and then we have our control signals here for RS, RW, and the LCD and the backlight, and our contrast level there. So those are the direct outputs to the LCD, to the HD44780, and then for our input signals, I'm just going to bring again the image of the Altera DE2 board just to talk about. Now what I've done is I've mapped a series of inputs to groups of switches on the DE2 board, and what we're doing here is we're using these to control either strings of characters within a character string, so a whole series of letters that essentially will send an entire series of characters onto the screen as one single message based on a particular state of these switches. So as you can see, we have a 4-bit input interface here. So various combinations of these switches based on how you code it within the strings within the VHDL code, you can have separate full 32 character messages being shown on the screen. And again, it's all based on the hexadecimal values that you have programmed within these character strings. That's what these 4 particular switches here are used for, and that's the way I've set it up with a specific state machine within the code that we'll review. And I did that specifically just for my own project, just to make it a little easier to control various messages being shown. Because essentially what I've done is I've taken an existing core and I've manipulated and added things. What it does have here is a series of input switches that are used here. These 8 input switches are used to control 2 specific characters. So we have, say for instance, character 1 and character 2, and based on the combination of logic levels on these 2 switches will essentially dictate 2 separate characters specifically, and what their value is. So as you're changing the logic levels on these switches, in real time the screen will change those character values. And that's happening because our VHDL code is looping in a continuous loop sequence. So it's essentially constantly scanning these switches and their logic states to either declare a specific character that will be displayed on the screen, or for these 4 here that I've added myself, they control a specific character string of letters, and essentially dictate an entire group of 32 characters for a full message to be displayed on the screen. And so we're going to go and review that and review the entire sequence of code and how it all works to implement that. So let's move into our VHDL code file now, and we'll review the code line by line just so that you understand. And again, this is all, you can download this, and after we've reviewed it, you'll know how to go in and manipulate it to create your own messages. And I'm going to do the best I can to lay this out in layman terms, but I do expect you to have some former VHDL programming experience, at least at the fundamental level, just so you can understand what's going on. So if you haven't had any experience with VHDL code, you might want to go and review it a little bit just so that you can follow along and not get lost. So essentially with any VHDL file, we have our IEEE libraries that are required for all the various functions that we use within the VHDL code. And we then move into our entity section of the code, which is essentially just where we map out our particular ports or pins or buses that we have and that we're using on our FPGA, or that we will be mapping to the FPGA. So these are ports that will eventually we will assign to the physical pins on the FPGA. So we're just assigning a naming convention or a name to a specific input pin as part of our FPGA and the VHDL design rather. So as you can see, we have all of our clock signals, our control signals for the LCD display. We have our databus, and then a series of input switches that we use that I have implemented to control the display of specific messages on the screen. And that's what these 4 signals here, these input pins, are assigned to a series of switches. And so based on their highs and lows, their logic high and logic low level, that will essentially dictate a state machine to display a specific message on the screen. And then you have these 8 switches here, which are actually part of the existing core, and they essentially control 2 separate specific characters to be displayed of a certain value based on their logic condition. So it's just a means, like you could say the first 4 switches would be the representation of a value on a character from 0 to 9, and then the second set would be the value of a second digit displaying the values from A to F based on their logic setup. So it's a way of implementing and displaying 2 characters showing a hexadecimal value on your display in real time as it's monitoring these particular pins that are hooked up to logic switches on your development board or part of your design that you have incorporated with your FPGA. So that's what the entity section does. It's just mapping all of our input ports and output ports. We then move into the architecture. And so the architecture section of our VHDL code, the first part of it here is before the begin statement, is essentially where we declare all of our various signals, the internally used signals within our VHDL or the FPGA. So essentially what that is it's basically internal signals that are, or variables essentially, which are not actually being interfaced to the FPGA ports, or the within our VHDL code where we actually have a port that will be eventually assigned to a specific output pin. If it's not being assigned to a specific pin and it's just an internally referenced signal, then that's essentially where we're declaring all of those various signals, whether it be a character string or an STD logic vector, essentially a bus, or a signal, a single logic line like STD logic. So that's this section here. That's the first section where we declare all those values. This area of the code here, we're essentially mapping internally used signals to a specific pin. So these particular signals that we've declared, there are specific ones that we want to actually interface to either an FPGA port or a data bus. Well, we can actually go and declare that specific signal line here, and we can actually map specific bits within that signal to a specific port that we've declared within our entity section of our code. So we can, that's all that the entire section of code here, all that's doing is just mapping those particular signal bits to a specific port that we have declared. So that's what this whole section here for. We're just mapping those to physical ports. I've then added a whole series of comments here that actually show you the hexadecimal equivalent to each of the various fonts or graphics that are available for the HD44780 LCD display. And they're just here for quick reference for you to copy and paste when you're creating custom messages of your own and assigning these values to the character strings, which we'll go and check out as we move down here. You'll see. So as you can see here, each of these areas of code is essentially a character string, and each of them are declared with a naming convention, which I've used LCD underscore display underscore string, and then a particular number for this particular character string. So as you can see, there's a whole series of hexadecimal values all in sequence or in an array, essentially. And each one of these hexadecimal values represents a character. And so if you, as you can see here, the hexadecimal value 42 represents the capital letter B. So if you were to go and scroll up here on the list to where the capital B is, you'll notice that it has a hexadecimal value of 42. And so that's where you can actually assign specific messages in this string of hexadecimal values. And whenever we call upon LCD display string 01, we're actually going to be calling this entire array of hexadecimal values. And so I've laid out a whole series of different strings with different messages. I've the first one here is Bluetooth link disconnected. The second one is Bluetooth link connected, which is the one that I actually used for my scan using my logic analyzer. And there's a whole series of them here with charging rates for if you're using a battery and you're charging a battery. You could have these particular messages be displayed at specific charge points, different things like that, but they're all completely customizable. They're all just labeled with a specific designator, 07, 06, the prefix there for you. So you feel free to go in and manipulate these as you see fit. And then you can go and manipulate the VHDL code when they call upon these particular strings. You can have your own custom messages embedded in these string values. So that's all these with these. This area of code is just representing all the different strings that we have that we can call upon to display specific messages. So this area of our VHDL code, essentially what this statement does here is essentially dictating that our data bus to our LCD display is actually a tri-state data bus. So if you're not familiar with a tri-state data bus, you might want to go and read up on that. And here we actually all we're doing here is mapping our LCD, our W or read and write port to a signal. We're just mapping that. So don't really have to worry too much about that. Here is our state machine. This is the state machine that I've added for mapping specific character strings to the LCD display based on a specific set of input states, logic states on input switches. So for the LCD car array, a series of inputs, which is a 4-bit interface connected to 4 separate input switches based on their logic states. So as you can see here, I move through all the various binary conditions that they can be in. And I don't go through all of them, but I have a certain number of them there. And based on their logic highs and logic low values, we'll determine which character string is being assigned to the FPGA. And as you'll see here, the parts of the code will be using this variable here, next car, within our code to map the LCD character data to the LCD display. But essentially this state machine, all it's doing is just assigning these particular strings to the data, the LCD display, based on the input switches that you have on LCD car array. So you have all the different states and all the different string messages that you can have that we were talking about earlier. So you have LCD display string 11, LCD display string 10, and so on and so forth. And based on these logic highs and logic low settings of switches, you can determine which LCD display string is being channeled to the LCD display. So that's what this whole state machine is used for. And that's just one that I implemented to make it a little easier to channel messages, entire 32 character messages onto the screen. And here we have our clock signal generation. And this is this particular process. We're not going to really go into this too much. I will have specific information on my website that will go over the timing requirements, and but essentially don't really worry about that for this part. Essentially this will handle all of the generation of the specific timing requirements that we need for the HD44780 to function with the state machines that we have implemented within our code. So if you want to go in and check all the timing requirements, I'll have all that information laid out on the website as well. So now we're actually moving into the actual the actual core of the VHDL code that we have. And we essentially start with a reset function. So whenever we have a specific reset signal being sent, it will actually prevent anything from happening to the LCD display. So that's all that is. And this is also part of our timing requirements of our clock. So we won't go into that too much right now. But here we're moving into our actual state machine that's used to map our hexadecimal values on our databus and our control signals on the LCD enable, LCD register select, and the LCD read-write line. And so essentially, as you can see here, this is where our initialization sequence begins. And this whole process of 8 different state machines, states, all 8 of these are all part of the initialization sequence. And so if you actually look, and I'll bring in my chart that I had, my text document where I went through the whole initialization sequence, you'll see that it maps and matches accordingly based on our hexadecimal values on our data bus. So here we have the 3 external reset signals, as we had here, that when we reviewed it, when we were looking at the actual logic scan and the data that we collected through the logic scan on the logic analyzer. You'll see these are the states on the state machine for the initialization sequence. And for each of the 8 states, they are all displayed here. And you'll see how their hexadecimal value maps and matches accordingly. We have our 08, 01, and 0C, and the final hexadecimal 06, as I had reviewed before. So it's pretty straightforward. So that's the entire initialization sequence. So all that part of the code is the initialization sequence. So essentially this area of our VHDL code, what we're doing is we're actually beginning to send hexadecimal value, character value, or character data to the LCD display. And now there's particular if and then else statements that we use here to control the conditions of a series of input switches that we have declared to control essentially 2 separate characters that are used instead of, say, hexadecimal variables within a string. We actually have them mapped to a specific variable, which I'll actually just scroll up and show you. You may have seen them, but you didn't really notice them. So up here under our string for LCD display string 11, you'll notice that the last 2 hexadecimal values, I've actually implemented these custom variables. So separated by our comma, and we have our X value to declare a hex value. all the way over to the next comma, you'll notice that there is a custom value here represented, a variable essentially. And what this is that this is essentially, if you essentially replace this particular variable for a particular hexadecimal number, you're actually controlling that particular character on the string to be represented by a specific set of switches that we've mapped to this variable. So whenever you would change the condition of, say, 4 switches, it would actually determine which character would be displayed for this particular character within our sequence on our LCD display string. So you can actually go in and create several of these if you wanted, and then you could map them out to different hexadecimal variables within your string values, and have those mapped to a series of input switches and have them display custom characters. So just make note of that. So this particular variable that I have laid out here, each of these is mapped to a specific series of input switches that we'll talk about there now. So this one here is for 7 down to 0, and then the last one here is from 3 down to 0. So now we'll go back down to our area there where I was declaring that, where we're actually sending the hexadecimal value. So that's what this area of code is doing, is just essentially dictating how those particular input switches that we have, how they're going to react, and we have them set up so that they will display the numbers from 0 to 9, and then the letters A to F, and representation of hexadecimal values. And whatever condition those particular sets of switches are set to, they actually send their condition and create essentially a custom hexadecimal value that is assigned to these custom-made variables here. And essentially all they do is replace your hexadecimal number to represent a character onto the LCD display within the LCD display string. So just remember that. And then we move on. We have a couple of more if-then-else statements, and all these are doing is controlling how the information that we're sending out to it is being controlled on the screen. So we have, as the comments are laying everything out in layman terms here, we have loop to send out 32 characters to the LCD display, 16 by 2 lines. And then whenever we're sending out, if it reaches, say, the area of the screen 15, it's going to jump to the second line. And then it will return to the first line if it reaches the end of the display. So that's all. These are just controlling, essentially, whenever as we move through our states within our state machine sending character data, it will automatically implement these controlling of our cursor. So the last section of our state machine is pretty straightforward. These are just control states where we actually send specific hexadecimal values to the databus, and specific logic highs and logic lows for our enable and our RS value for a particular state that our state machine is in. So whenever we're on line 2 state within the state machine, it's actually all it's doing is setting the right address to send the cursor to line 2 on the first character. And then the same goes for the return home state. We're sending essentially returning the right address to the first character position on line 1. Now, as you'll notice, the databus value that we have here is C0, which is to set the right address to line 2 character 1. From my text document here that we were reviewing earlier on, you'll notice how these values match the set DDRAM address, which is essentially exactly what they're doing. So we have our C0 and our 80 hexadecimal value 80 for those corresponding commands. And then we have our drop LCD state, which all that's doing is essentially dictating and telling the state machine to create a falling edge on our LCD enable line, and then to declaring the next state to be a hold, which is this particular state here. Now, I want to mention this, depending on the core that you're using, sometimes they don't include, if you're using a backlight on your LCD, some LCDs have backlights, some of them don't. So just make sure that whatever logic line you're using to drive and activate your backlight, make sure that you add this particular statement for your backlight to be activated, and also your LCD contrast to be activated as well, because sometimes those aren't included, and this would prevent any information from being displayed on your screen if you didn't have the actual LCD circuit for your contrast to be enabled during that hold line. So just make sure you have those included and you should be fine. So that concludes the end of our VHDL code review. Before we go, I want to actually go over just very quickly go over the declarations for when we assign the actual ports from our VHDL code design, where we assign these port names to specific pins, physical pins on the FPGA. But I will include this port declarations chart, which dictates which specific variables that are used for the Altera Cyclone II, which is part of the Altera DE2 board. And so you'll be able to map, using this, you'll be able to map your specific ports that you have declared within your VHDL code. You can map those to the specific pins that are a part of the Altera Cyclone II for the DE2 board. So again, I will include this for download on the website for you, just so you can map those accordingly if you're using a different software package like Altera Quartus, and you'll be using that within Pin Planner to map those specific pins to your ports.